In the last lecture, we have discussed about various non-contiguous memory allocation techniques such as paging and segmentation. In this lecture, we will discuss about virtual memory, implementation of virtual memory using demand paging and various page replacement algorithms. We will start with virtual memory. We have already discussed various contiguous and non-contiguous memory allocation techniques like fixed partitions, variable partitions, paging and segmentation. Using any of these techniques requires that the whole process should be loaded in memory before its execution starts. That means, the entire process had to be stored in memory somewhere. In practice, most processes do not need all their pages during its lifetime, or at least not all the pages are required at once for several reasons. First reason is error handling code is not needed unless that specific error occurs, some of which are quite rare. Second is arrays are often oversized for worst case scenarios and only a small fraction of the arrays are actually used in practice. Third is certain features of certain programs are rarely used, such as if you are working on MS Word program, many of its features like mail merge, templates, etc., are rarely used. One of the possibilities is to load some portion of a process actually needed, and when we require other unloaded parts of the process, those can be loaded dynamically. The ability to load only the portions of processes that were actually needed has several benefits. First is programs having much larger address space than actual physical memory existing on the computer can be executed. Because each process is only using a fraction of its total address space, there is more memory left for other programs, improving CPU utilization and system throughput. Third, as only a small portion of the processes is loaded in memory, less input output is needed for swapping processes in and out of memory. This increases the speed of system. Running a program that is not entirely in memory would benefit both system and user. Virtual memory is a technique of memory allocation that allows the execution of processes that may not be completely in memory. The operating system keeps those portions of the program in memory that is currently in use, and rest of the program remains on the secondary storage without affecting the program execution. If during execution process reaches at the code which is not in memory, the operating system loads the required portion of code in memory from secondary storage and execution proceeds. It allows programmers not to worry about limited memory, and user thinks that there is infinite memory available to run its programs. This figure contains the general layout of virtual memory, which can be much larger than physical memory. Here, logical memory or virtual memory contains n pages. Only few of the pages have been loaded and corresponding entries have been made in memory map. Physical memory is smaller than virtual memory, and data is transferred dynamically between physical memory and secondary memory. Since the program can be loaded in parts, therefore, virtual memory can be implemented using only and any of the non-contiguous memory allocation techniques such as paging, segmentation and paging with segmentation. Paging is most suitable for implementing virtual memory using demand paging. Now, we are going to discuss what are advantages of virtual memory. First advantage is program size can be more than the size of total main memory. Second is it saves memory as only required portions of a process are loaded and other remain on hard disk. Third is each user program could take less physical memory, therefore, more programs can be loaded simultaneously, increasing the utilization of CPU and input output resources. Fourth is virtual memory does not create external fragmentation, but it may cause very little internal fragmentation. Very heavy softwares like MATLAB and Visual Studio requires a lot of memory to load. Using virtual memory, not only can load these heavy programs simultaneously, but other programs like Internet Explorer, MS Word, etc., can also run along with these programs using virtual memory. Next is dynamic linking and sharing of code and data is also possible. Seventh point is, since it is not required to load whole of the program in memory, less number of input output operations would be needed to load or swap each user program into memory. There are some disadvantages of virtual memory. First is it requires complex hardware support. Second, program runs slower, which can reduce performance. Third is it takes more time to switch between processes. Fourth is it makes program execution time less predictable, and last one is virtual memory makes address translation much more complicated. Next, we are going to discuss demand paging. A demand paging is similar to a paging system with swapping. When we want to execute a process, we swap it into memory. When a process is swapped in, all of its pages are not swapped in at once. Rather, pages are swapped in only when the running process needs them. This is termed as a lazy swapper or a pager. A lazy swapper does not swap in any page until running process requires it. When a process is to be swapped in, the pager guesses which pages will be used for initial execution of the process. Instead of swapping in whole process, the pager brings only those necessary pages into memory. Thus, it avoids reading into memory pages that will not be used in any way, decreasing the swap time and the amount of physical memory needed. Hardware support is required to distinguish between those pages that are in memory and those pages that are on the disk. This is done using the valid or invalid bit scheme as shown in figure. The valid bit in page table corresponding to any page indicates that the page is available in memory and process can use it for execution. The page number 0, 2 and 5 are available in memory, but if the bit is invalid, this indicates that the page demanded is out of virtual space or page is not in memory. That means, pages that are not loaded into memory are marked as invalid in the page table. While the process executes and accesses pages that are available in memory, execution proceeds normally and exactly as if all the pages were loaded into memory. On the other hand, page fault trap is generated if a page is needed that was not originally loaded up. This trap is the result of the operating system's failure to bring the desired page into memory. That means, the operating system has not loaded the desired page in memory to save memory and bring minimum pages into memory. Page fault can be handled in a series of steps as shown in figure. The first step is the memory address generated by CPU which has caused page fault is first checked in page table to determine whether the reference was a valid or invalid memory access. Second step is, if the reference was invalid, process is terminated. If it was a valid memory reference, but we have not yet brought in the required page, we must bring the page in memory and start paging activity. To load a page in memory, we find a free frame. A free frame is located possibly from a free frame list. Fourth step is we schedule a disk operation to bring in the necessary page from disk to free frame. This will usually block this process as it requires input output operation, allowing some other process to use the CPU in the meantime. Next step is when the disk read is complete, the page table of process is modified with the new frame number and the invalid bit is changed to valid bit, indicating that this is now a valid page reference. That means the desired page is available in memory now. The last step is after step 4, the CPU started executing some other process. When this process gets its turn on CPU, the instruction of this process that caused the page fault must now be restarted from the beginning. The process can now access the page as though it had always been in memory. The interrupted process which has caused page fault can be restarted from the same instruction where it caused page fault. The difference is only that at the time of restarting the same instruction again, the desired page is in memory. This makes the running of large processes possible using virtual memory. On the extreme end of this technique, we can start executing a process with no pages in memory. This is called pure demand paging. No pages are swapped in for a process until they are requested by page faults. In pure demand paging, as the process starts its execution, immediately it generates page fault. As the process executes, page faults occurs for the pages not in memory and the corresponding pages are loaded into memory. Now, we are going to discuss performance of demand paging. If operating system can guess correctly and bring in the required pages into main memory before the start of process, the execution proceeds normally and we have no page faults. In such case, effective access time is equal to the memory access time. However, if some page fault occurs due to non-availability of page in memory, secondary storage access is required to load the page. Accessing of secondary storage to deal with page fault makes the execution of process slow and system performance decreases due to this. Let us suppose that a normal memory access requires 200 nanoseconds and that servicing a page fault takes 8 milliseconds, that is 80 lakh nanoseconds or 40,000 times a normal memory access. With a page fault rate of p on a scale from 0 to 1, the effective access time is shown in figure. Effective access time depends heavily on the value of p. Even if only one access in 1000 causes a page fault, that means p is equal to 0.001, the effective access time drops from 200 nanoseconds to 8.2 microseconds, a slowdown of a factor of 40 times. In order to keep the slowdown less than 10%, the page fault rate must be less than 0.000025 or 1 in 3,99,990 accesses. Next, we are going to discuss various page replacement algorithms. In order to take the maximum benefit of virtual memory, we load several processes into memory at the same time. Since we load only those pages that are actually needed by each process at any given time, there is room to load many more processes. For example, let we have 10 programs each having 20 pages. If we have memory containing 50 frames for user processes, then only 2 processes can be loaded as full. However, if every process is required only 5 pages to be loaded to start its execution, we can load as many as 10 processes in memory using virtual memory. Now, what happens if some running process suddenly requires more pages and there is not any free frame available to load it? There are several possible solutions to consider. First is terminate the process. Since we are trying to improve the system utilization and throughput, terminating a process is not a good solution. Second is put the process requesting more pages into a wait queue until some free frames becomes available. Third is swap some process out of memory completely, freeing up its page frames. The free frames can be used by other processes and system can continue to work. Fourth is find some page in memory that is not being used right now and swap that page only out to disk, freeing up a frame that can be allocated to the process requesting it. This is known as page replacement and is the most common solution. Whenever a page fault occurs and there is no any free frame to load a new page, page replacement is required. Page replacement activity contains following series of steps to be performed as also shown in figure. First step is find the location of the desired page which caused page fault on disk, either in swap space or in the file system. Second step is find a free frame. If there is a free frame, use it. If there is no free frame, use a page replacement algorithm to select an existing frame to be replaced, known as the victim frame. Third step is write the victim frame to disk, change all related page tables to indicate that this page is no longer in memory. Next step is read in the desired page and store it in the frame. Adjust all related page and frame tables to indicate the change. Fifth step is restart the process that was waiting for this page. There are many different page replacement algorithms. We evaluate an algorithm by running it on a particular string of memory reference and computing the number of page fault. First algorithm is first in first out. The simplest page replacement algorithm is a FIFO algorithm. A FIFO replacement algorithm associates with each page the time when that page was brought into memory. When a page must be replaced, the oldest page is chosen. We can create a FIFO queue to hold all pages in memory. The working of FIFO algorithm with 3 available frames on reference string 7, 0, 1, 2, 0, 3, 0, 4, 2, 3, 0, 3, 2, 1, 2, 0, 1, 7, 0, 1 has been shown in this figure. The first 3 references 7, 0, 1 are compulsory page faults. As the algorithm proceeds, new pages are brought in and added to the tail of a queue, and the page at the head of the queue is the next victim. In the example shown in this figure, 20 page requests result in 15 page faults. FIFO throws out oldest page and is fair to pages, allowing them to live in memory for same amount of time. FIFO is not good because it may throw out heavily used pages instead of infrequently used pages. Second algorithm is optimal algorithm. An optimal page replacement algorithm has the lowest page fault rate of all algorithms. An optimal page replacement algorithm is also called as opt or min. It uses a simple rule to replace the page that will not be used for the longest period of time. Now, consider the same example string with 3 empty frames. The reference to page 2 at 4th position in reference string replaces page 7, because page 7 will not be used until reference at 18th position, whereas page 0 will be used at position 5 and page 1 at position 14. The reference to page 3 at position 6 replaces page 1, as page 1 will be the last of the 3 pages in memory to be referenced again. Optimal replacement is much better than a FIFO algorithm. The optimal page replacement algorithm is difficult to implement because it requires future knowledge of the reference string. Third algorithm is LRU algorithm. The FIFO algorithm uses the time when a page was brought into the memory. The OPT algorithm uses the time when a page is to be used and it looks into the future uses. LRU algorithm replaces the page that has not been used for the longest period of time. LRU replacement associates with each page the time when it was used last time. When a page must be replaced, LRU chooses that page that has not been used for the longest period of time. This figure illustrates LRU for our example string yielding 12 page faults as compared to 15 for FIFO and 9 for OPT algorithm. Let R be the reverse of a reference string S, then the page fault rate for the LRU algorithm on S is the same as the page fault rate for the OPT algorithm on R. Counter and stacks can be used to implement LRU algorithm. Next algorithm is LRU approximation algorithms. Some systems provide no hardware support and other page replacement algorithms must be used. Many systems provide some help, however, in the form of a reference bit. The reference bit for a page is set to 1 by hardware whenever that page is referenced. Reference bits are associated with each entry in the page table. Initially, all bits are cleared to 0 by the operating system. As a user process executes, the bit associated with each page referenced is set to 1 by the hardware. We do not know the order of use, but we know that which pages are free and which are used. This knowledge can be used to develop many page replacement algorithms like additional reference bits algorithm, second chance algorithm and enhanced second chance algorithm. All these algorithms approximate LRU replacement. Last algorithm is counting algorithms. There are several algorithms based on counting the number of references that have been made to a given page, such as first is LFU algorithm, replace the page with the lowest reference count. This algorithm suffers from the situation in which a page is used heavily during the initial phases of a process, but then is never used again. Second is MFU algorithm, replace the page with the highest reference count. The logic behind this idea is that pages that have already been referenced a lot have been in the system a long time and we are probably done with them, whereas pages referenced only a few times have only recently been loaded and we still need them. Lastly, we are going to discuss thrashing. If a process cannot maintain its minimum required number of frames, then it must be swapped out, freeing up frames for other processes. But what about a process that can keep its minimum, but cannot keep all the frames that it is currently using on a regular basis? In this case, it is forced to page out pages that will need again in the very near future, leading to large number of page faults. In worst situation, For every logical address, a page fault occurs. A situation when processes spend more time in paging activity than executing them is said to be thrashing. The high paging activity is called thrashing. Finally, we have conclusions. With the help of virtual memory, it is possible to run a process whose logical address space is larger than the available physical address space. Virtual memory increases the degree of multiprogramming and increases CPU utilization. Virtual memory is commonly implemented by demand paging. Demand paging loads the page in demand and whole process is never loaded in memory. Pure demand paging never brings in a page until that page is referenced. If total memory requirement exceeds the capacity of physical memory, then page replacement is done to replace pages from memory to free frames for new pages. Various page replacement algorithms are used, each having its own advantages and disadvantages. Thanks.